doubts in it? No, right? Okay, so all good up to there? Are we good to proceed and go and look at the next topic under complex numbers? Yes, okay. Then what I thought of doing today, we might be able to finish this. Let's see. Let's look at, let me go to the board. Now, with this new knowledge of complex numbers, right? Think back on all the other mathematics that you learned with this new knowledge now about numbers, okay? For example, I think the simplest piece of mathematics that you can think about, but don't think of how would calculus now work? How would differentiation, like, before you think of those things, like think of some simple piece of math, like something in algebra, like solving an equation. Now look back and think, so does this mean when we solve equations all this time, every time we just got real number answers? All the answers we got after solving an equation were real numbers. X equals 5, X equals 10, X equals half. But this means there could be equations where solutions are complex numbers, where solutions have I in them, right? And if you remember, that's how complex numbers were created when people were stumbling on equations where solutions didn't make sense, right? So we are going to look at polynomial equations. So when I say polynomial equations, something should quickly run through your mind. Polynomial, linear equations, quadratic equations, cubic equations, quartic, polynomial should quickly awaken a certain memory. You have different types of polynomials depending on the highest degree of x. So you start with, if the degree of x is 0, it's a constant polynomial like 5, or you can have linear polynomial where the highest degree is 1, highest power is 1, like 2x plus 3, and then quadratic, and then cubic and quartic and so on. And then if you have such expressions in an equation, we call those equations linear equation, quadratic equation, cubic equation, and so on. And we have learned up to quadratics how to solve linear equations. No, Malit? No. Malit, can you put that question to everyone, please? Now, especially when you're asking a question related to the lesson, I know like it's by default, you must have just a message to be sent to me. That's why you have to change that setting. Can you say it to everyone, Malit? Okay. What do others think about Malit's question? He's asking about what a polynomial is. He thinks that a polynomial is when you have more than one x term Can someone give an answer to him? A polynomial takes this form. I'm writing it, if I write it from the back, and you will see why I'm writing it from the, okay, let me write like this. A x to the power of, this is a polynomial of degree n. I'm sure I enlightened y'all with this. It's just that you can't attain enlightenment twice. If you're enlightened once, that's it. Then you can just have to refresh if you have forgotten. Plus B. Here I'm using the letters A, B, C, the simple letters of the alphabet to represent coefficients of terms. So ax to the power of n plus bx to the power of n minus 1 plus c x to the power of n minus 2 plus, you can see what's going on here, n minus 3 plus da 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 plus finally it'll drop to let me say C, D, E. I will maybe I have gone up to like P and it has no X. This is the format of a polynomial, like the form of a polynomial. It's a collection of terms, Here, these are the terms. This plus this plus this plus this plus da 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 plus this. It's a collection of terms. What kind of terms? Terms with different whole number powers of x. Whole number powers of x. So for example, and we usually, when you write it out, you write the terms so that the powers are descending. That's not a must, but we always like to keep things pretty. So for example, you can have 2x to the power of 5 minus 4x to the power of 3 plus 8. This is a polynomial. Now you might ask me, where is the power? I just said the powers must descend. Where is the term with power 4? Okay, you have 3. Where is the term with power 2? Where is the term with power 1?
0.
What does that mean?
Coefficient is 0. So then
0. Very good. Yes, Malik. Okay. So this is something that has this form. So it's a polynomial. It doesn't have any restrictions on how many terms you should have. It's just a bunch of a collection of terms. I mean, even if you have one term, like 4x to the power of 9, that's a polynomial of degree 9. All other terms, no other terms. Malit, is that clear?
Yeah, then miss, what's binomial?
Good question. Okay, so you have, okay. So first thing, polynomials are given. The polynomial stuff. Now we have not come to the topic of the day yet. We are talking about polynomials, okay? Because you can't remember. When you have polynomials, one way in which they can be given names is by thinking about the degree. That's what I just talked about. What do you mean by degree? Highest power of x. That's one way that you can categorize or label polynomials. If the degree is 1, degree and the name, okay? If the degree is 0, we say it's a constant polynomial, constant p polynomial, right? If the degree is 1, we say it's a linear polynomial. Degree is 2, we say it's a quadratic polynomial, QU, quadratic, and so on, cubic, and so on. You can also name polynomials depending on the number of terms they have. By thinking of the number of terms it has, let me say the number of terms it has. Okay, so number of terms and the name. So if a polynomial has one, you can't have no terms, so then you don't have anything. If you have one term, it's called a, who can remember? Yes, Hatvi. A polynomial with one term is a monomial, like monocycle. With one wheel, one tire, whatever. Monomial. 2 terms,
So then polynomial is just more than 2 terms, right?
I just said here. What did I just say here? What did I just
and then when you brought the table, I kind of got okay, miss, you just continue.
So this, wait, okay. So two terms binomial. Here, if a polynomial has one term, it's a monomial. Poly means many terms, no? Poly means many. So that number can be any number. So starting with 1. I mean, if you can have one term in your polynomial, or 2 terms, 3 terms, 4 terms. So if you have 2 terms, binomial. If you have 3 terms, trinomial. If you have 4, I don't know. I don't think we have a name after that. I'm not sure, okay? But the point is this. So there are 2 different ways in which you can label them. So for example, if I have, look at this polynomial, 2x squared, okay? It's a quadratic. It's a quadratic polynomial. It's a quadratic monomial. You understand? This is a quadratic monomial. We usually don't, a lot of the times we don't use these words, but this is a commonly used. You know, we come across this a lot because we have binomial expansion. We learn how to expand a power of a polynomial that has 2 terms. So it's called binomial expansion. So I mean, you can use these 2 names in combination. So you can call this, it's a quadratic monomial. This is a quadratic binomial. You understand?
Yes, miss. I understand.
Have 5x plus 2. That's a linear polynomial. We are more interested in the degree, right? So you see, it's a linear polynomial. It's a linear expression. And it also happens to be a binomial, 2 terms. Like the number of terms is not of big significance. Like, think about it. I mean, we don't care how many terms it has, but what's important is the degree. That has so many connections. For example, if you think of an equation, that degree tells you how many solutions you're going to have. But the number of terms, I mean, it's not very useful, or it's not a big thing. So we have names for it when we use them when needed. But these are the degree, the names related to the degree is what's important. Okay, enough, no polynomial lesson.
Yeah, I remember.
Okay, so
thank you.
You're welcome. What we are going to look at today is how there can be equations who has complex solutions. Okay, so put a topic. Polynomial equation. This is a subtopic. Polynomial equations solutions. Can I ask you something like that? Not very important. Do you prefer this whiteboard or the grid whiteboard? The, what do you call it? The Windows Windows whiteboard, or this? This okay.
Anything, both are good.
Both are good. Okay, I'll stick to this. Polynomial equations whose solutions are complex numbers. I mean, okay, let's just okay. Now remember, real numbers are also complex numbers, right? But now we are talking in general, like it could be real, imaginary, or something like the vanilla chocolate combination, like anything. Earlier we just had real. Now we are talking everything together. So when I say complex numbers, even when the solutions are real numbers, those solutions are complex numbers, right? But more specifically they are real numbers. Okay. So this is nothing new. We will just look at some equations where the solutions are complex numbers. We're not learning anything new. There is one thing in new. There is a little theorem, just like when we were learning how to find the square root of a complex number. We started with a little theorem like that. We have a little theorem here to write in the beginning because we will be using this. So theorem. Okay. Let's write this theorem. Very useful theorem. Where is my... Okay, I will give you actually two theorems. One you already know, but let us just recall this. So two theorems. Actually, this first theorem that I'm going to give you is called the fundamental theorem of algebra. So for whole of algebra, this is like the basic, the first, most it's called fundamental theorem of algebra. Okay, if you like, you can put in brackets. This is the fundamental theorem of algebra. That name is cool. This is the fundamental theorem of algebra. For different areas in mathematics, there is this fundamental theorem of. So there is a fundamental theorem of arithmetic. You find out what that is. What you're going to write now here is fundamental theorem of algebra. There is a fundamental theorem of calculus. It's called fundamental theorem of algebra. Okay, what does this theorem say? You already know this. It says that a polynomial equation, here this is the theorem, a polynomial equation of degree n, if the degree is n of a certain equation, it should have how many solutions? You already know this. If the degree is 1, if you have a linear equation, how many solutions would you expect it to have? Linear equation like 2x plus 3 equals 5. So usually when you think of the equation, you put all the terms to one side and say equal to 0. So if this polynomial is linear, how many solutions would you have? So 2x plus 1, right? For example, 2x plus 3 equals 0 would have one solution. Graphically, you know why that makes sense. This represents a straight line, and solutions are where the line cuts the x-axis. So a straight line only cuts the x-axis once. Makes sense. If you have a polynomial of degree 2, if your p of x equals 0, if this is 2x squared plus 3 equals 0, you would expect to have how many solutions?
2.
2, because it's a parabola. Now you need to think about this, okay? And a parabola cuts the x-axis at 2 places, but you know that earlier that we had cases where the parabola would be like hovering above the x-axis, so they
Has a 1 point also.
Can have a, so that when it touches the x-axis, the roots are repeated, same root twice. So there are 2 solutions. It's the same. The solutions are the same. X equals 2 and x equals 2. But earlier we had a case when the parabola was, if it was like that, there were no solutions still. But we say there are no real solutions, okay? But there has to be 2. If the order is 2, order or degree, there is another word for degree is order. I use both, okay? Both words, order or degree. If the order is 2, there must be 2 solutions. If the order is 3, there must be 3 solutions. So this is the fundamental theorem of algebra. a polynomial equation of degree n has n roots. Minimize this. Has n number of roots. I'll say n number of roots. So for those equations, for those quadratic equations that you said there are no real roots. Oops. Now you have to understand, but we just said that there are no real roots. It has to have roots. 2 roots it has to have. Any quadratic will have 2 roots. What happened in that verse? It was just that the roots were not real. They are complex. Okay. And now we will be finding those. Very good, Hatya. I'm just seeing your message. You are saying 2 at most. 2 real solutions at most. N number, then there will be n solutions. We were saying at most earlier. I'm glad you remembered that. That is for real roots. Okay, here's a second theorem. Now we need both these theorems when we look at equations whose solutions will be complex numbers. Theorem 2. This will also kind of make sense to you. No, you still don't know this. Okay, this is new. Okay, let's write it. Wait, this is not a good. I had a better version of it. What is that? Let's try this. Okay, in red. Let me reword this, okay? For a polynomial, for a polynomial, with real coefficients, with real, let's put capital R. Why do we put capital R for the word real there? We are talking about not just the word real. We talk about real, the mathematical term real. Oh, wait, Patri, theorem is the plural of theory. No. Theorem is not the plural of theory. As you said, theories is the plural of theory. A theorem is a
Rule.
like a rule, yeah. It's a, no, I'm just thinking how to differentiate it with a theory.
The statement.
Theory, yeah, it's like a it's a proven
Fact.
Fact. Thank you, Nathan. Thank you.
It's more like a solid expression for something in maths.
It's a rule. I think that fits. It's just a single thing. When you say a theory, that's a bigger thing. Now, it's a theorem is a piece of fact. Yeah, it's one piece of fact. Like Pythagoras theorem, it's just one fact. When you say angles in a triangle add up to 180, that's a geometric theorem. It's a theorem. Theorems are facts that are proven so that you can use it over and over again. A theory, on the other hand, like relativity, is a theory. It's a broad, it can be a lot of theorems and a lot of things together to describe a certain phenomenon. We have Newton's 3 laws. That's a theory that explains how motion and forces and all related. So it's a broader, huge one. A theorem is just one fact, one thing. Okay. Good question. I like it because I don't think we have discussed what this word theorem. We just use it. Theorem. I think the first time it must have come up was when you were learning Pythagoras theorem, na? Yeah. So you have to know the meaning of every term that you are using. Okay, for a polynomial with real coefficients, shall I? I'm still wording it in my head because I don't like the way it is written here. Wait, don't write. I'm going to change this a bit. Let me get it right, and then you can copy it. Let me say if a polynomial has real coefficients. Let me change. I'm very sorry. I think you must have already written, but don't write still. Let me finish it first. If a polynomial has real coefficients and has a complex root or a complex solution, are you comfortable with using the word root? If a polynomial equation has real coefficients and has a complex root, then its conjugate is also a root. In other words, let me finish up, then you can copy. Oh, what is that, Malik? Oops. Yes, this is the official definition of the, okay, in Google, okay. So people can look at it. That's very good. Whenever you come, you do this all the time, right? You Google it, yeah. Then its conjugate is also a root. That is, this means, change color. This means complex roots occur in pairs. I like this. It's like forces occur in pairs. Okay, now I'm done. You can copy it. And while you copy this, just think about what this is saying. This is about polynomial equations that has real coefficients. You will not get where coefficients are complex. Now you have to think, everywhere you were having real numbers all this time, there could be a complex number. So when you write now, when you take for example, when you take an example for an equation, when I say 2x plus 3 equals, I said earlier, no, 2x plus 3 equals 0. Now these 2 and 3, these are coefficients now. These coefficients can be complex now. this could have been 2 plus 3i times x plus 4i equals 0, right? But we are not talking about that type of polynomials. We're talking about polynomials where the coefficients are real numbers, but its solution could be complex. I hope it's clear to you what I'm saying. Okay, so this theorem is about polynomials whose coefficients are real numbers. Then, if such a polynomial equation has a complex root, definitely its conjugate will also be a root. You will never get a single complex root as a root. Like they always occur in pairs. For example, if 2 plus 3i is a solution of a certain equation, 2 minus 3i will also be a solution. Buy one, get one free. If you know one solution, the other one, automatically you know, is 3 plus I a solution of that? Then 3 minus I would also be a solution according to this theorem. You understand? This happens only for complex roots, okay? A plus bi type roots, vanilla chocolate roots. I mean, no, it's for any complex root. If a polynomial equation has real coefficients and has a complex root, then its conjugate is also a root. Done writing?
Yes.
Now we will see how these two are applied in these polynomial equations that we are going to look at. Okay, here's your first. Did you understand the second theorem?
Yeah. I'm still trying to wrap my head around the.
Okay. Let me explain. And you will anyway see it when we look at our examples. So, for example, what I'm saying is this: say you have a quartic polynomial 2x power of 4, right? Quartic means power 4 minus 3x cube plus 4 is equal to 0 something. I'm just suppose take this equation and suppose I'm not solving it, but suppose. So how many solutions should this have? This should have 4 solutions. Okay, 4 solutions. There could be repeated solutions. There could be, right? Suppose I tell you that x equals 1 is a solution. Now fine, x equals 1 is a solution. 1 is a real number.
Okay.
Pure real, right? Pure real. What's the conjugate of 1? Even real numbers are complex now. So I can talk about the conjugate of 1. What is the conjugate of 1?
Just 1, right?
Very good, Nathan. Yeah. Very good. It's on the mirror. Conjugates are like, if you think of the real number line as a mirror, like the water surface, air and water, like it's separating 2 medium. For any point on above has a mirror below. Those are the conjugate pairs. But if a number is on the surface, that itself would be its conjugate. I mean, so conjugate is 1. So if I apply the theorem, I have, so one solution is 1. Can I make it 2? Because I keep saying one solution is 1. That sounds. If one solution is 2, according to the theorem, the conjugate, so it's the same thing. So it's done, right? But if I say, okay, there is another solution, x equals 3 plus 2i.
Then it is 3 minus 2i.
There is another solution. Is there is another solution 3 minus 2y because they occur in pairs. If one complex is a solution, its conjugate would automatically be a solution. Okay, so that's that. So you understood, Nathan. Very good. Okay, so let's look at let's look at some examples now. Hati is asking, like finding solutions for trigonometric equations. What's the connection? Like finding solutions for trigonometric equations? Yeah, okay. So for a trigonometric equation, there are infinitely many solutions all the time. All the time, infinitely many solutions. So we restrict the, when you are asked to solve an equation, they give you, find the solutions in this range. They give you a range in which to find the solutions. And then, so if they give you a one whole cycle, within 360 degrees, yes, you always, within 360, you always get two solutions. Yeah. Is there does it sound similar to this? Not really, isn't it? I don't know. I'm not sure. I don't know. Anyway, so let's look at some example. Okay. Example number 1. Please. Now remember the two theorems, keep them in your mind, and we'll look at some equations and we'll try to solve them. Example number 1. Solve, and the other thing you have to notice now is solve. Please, can you move back to the last slide? Of course, ma'am.
Okay, miss. Thank you.
Solve. Notice how I write the equation. Here's my equation. I'm not going to write x. What am I going to write instead of x? Now, usually x represents the variable or the unknown. Now I'm going to use, instead of x, z. Very good, Nathan. 2z squared. So it looks weird, okay? This is just like 2x squared. But we write 2z squared because z represents any complex number. Z is the standard notation to represent a complex number. 2z squared minus z plus 3 equals 0. So now don't panic. This is just a quadratic equation, okay? And we all know how to solve quadratic equations. There are several methods. If it factorizes, we can factorize. If it doesn't factorize, you use the quadratic formula. That's it, okay? So let's see here. Answer. You will see that this doesn't factorize. You can try a bit. Or does it? Does it factorize? Did I take a? If it factorizes, so then the solutions will be real. Does it factorize? Can you factorize this? No, you can't.
Not really. No.
Okay, so that means we will use the formula. So A is 2, B is -1, C is 3. These are the coefficients of the three terms, A, B, C. So let's use this in our formula. Z equals, not X, Z equals minus, what's the formula?
B minus B plus or minus root B squared minus 4AC over 2A.
Very good. Can you plug in the values now? And let's compute this, see what we get. you can try can you try computing this to see? Now you know that without solving, we can determine beforehand how many solutions, how many real solutions it's going to have. You will see if you use this discriminant, discriminant is negative, which tells us that there are no real roots.
Oh, I'll do that.
Check the discriminant. Do a small check of the discriminant.
Discriminant.
B squared is minus 1 squared minus 4 AC 1 minus, isn't it?
Let's see. Minus 23.
Yeah, no real roots, huh? But no real roots. There are two roots. Always there are two roots, but both roots are going to be what? Complex numbers. That's why. Okay, so let's see. I'm going to put the values in this formula. Okay, let's do it together. Minus b is minus 1 is 1, plus or minus. I just found b squared minus 4ac here, so I will just put minus 23. Root minus 23 over 2a. 2a is 2 times 2, that's 4. So 1 plus or minus 23 over 4. Okay. Earlier we would, for this we would say, this is absurd, this is nonsense. There are no negative roots. So no, we would say no solutions, or what we mean is no real solutions. But now we know how to go about this. We know how to tackle this. Let's write, yes. This is what it is. Yes, you can write it as, it is
23i.
Yeah, very good. How do you get that? So this is plus or minus.
No,
you can write this as
root 23i.
23 times
minus 1.
Minus 1.
Yeah.
Or I will show you it in a, wait, I will show you it on a side in a different color and bring it here. Okay, let me not write it here. I will first do it on the side here. My root minus 23, I can write as 20, I can separate out under the square root. I'm writing 23 times minus 1. Then, oops, that is same as root 23 times root minus 1. These are rules of surds. Make sure that you understand what I'm doing in each step. This step I just wrote minus 23 as 23 times minus 1. That's completely okay. I can do that. And then this is a rule. If I have square root of the product of two things, I can separate it out as square root of this times square root of that as two surds. And then what I have here is, this is root 23 times, this is I. So this is root 23 I. Malik, now solving equations like discarding the multiverse of, yeah, isn't it? Okay, so I can write this as 1 plus or minus. I can write my answer in a plus bi form. So quarter over root 23 over 4 I. So what are my two answers? Therefore, the solutions are, Z equals quarter plus root 23 over 4i. Do you see the conjugates? Quarter minus
1 over 4 minus 23 over 4i.
If this is a solution, that would be a solution, and we got both of them here. So these are complex roots. there is something in this. Did you understand? Did you understand? There is something in this that I want to like talk about and show you, but I will just keep it for later. Okay. Right. Shall we look at another example? Are you ready?
Yes, indeed.
Okay. I'll go to the next page. Example 2. Given that x equals -4 is a solution of I'm going to bring x, I'm writing in terms of x again, just to show you that it doesn't make a difference. But why we use z in equations is when we know that, like it is to give you a hint that there are complex solutions for this equation. So I'm already using z for the unknown, as the letter to represent the unknown. But even if you have x, no problem, right? X cubed plus 2x squared, now this is a cubic, minus 11x minus, what is this, minus 12? Minus 12 is equal to 0. Given that x equals -4 is a root or a solution of this, find the other solutions. Find the other solutions. Find the other solutions. Find the other solutions. Now, I don't know whether on the other side you are kind of panicking. You are giving us a cubic. We haven't learned how to solve cubic. We know how to solve cubic. If we know one solution, you know how to do it. This we learned in P3 under algebra, polynomials. Yeah, polynomials, factor theorem and all that. Okay. Right. How do we go about this? Any polynomial.
Can I like explain?
Yes, yes, Malik, yes.
So since x equals -4 is a solution of the equation of the polynomial we've been given, then we can make x -4 also a term. We put the 4 to the other side and then it becomes x plus 4. And then we can divide the equation we have here by that by x plus 4, and then we can get the quadratic, and then we take the quadratic roots to find.
Very good. Correct. So any polynomial of degree 2 and above, we solve by factorizing. Like how do you solve a quadratic? By factorizing. So cubic means there should be 3 linear factors. A quartic means there should be 4 linear factors. If you can factorize your polynomial by equating each factor to 0, you can find your solutions. That's what you do. Now here one solution is given, so you know one factor. If x equals -4 is a solution, that means x plus 4 is a factor of this polynomial. What I have on the left hand side, x cubed plus 2x squared minus 11x minus 12. X plus 4 is a factor of that. Then by dividing this polynomial by that factor, I can get the other 2 linear factors together as a quadratic. And when I have that quadratic, I can factorize it, or I can take care of that separately. Quadratic, you can find the other 2 solutions. So I'm going to write out all the steps here just for you to just for your knowledge, you can either copy my steps or you can just do it if you know, like Malit said, if you already know how to do this. But I'm going to just write what I have is this. This is the solution, this is the answer. So I want to factor, if I'm to solve this, I need to factorize this. But one factor I already know, it's x plus 4. And the other factor, there should be a quadratic. Quadratic factor. Okay. Now, how did I write this step? Let me write in brackets. Since x equals minus 4 is a solution. Now, let us find this quadratic factor. How can I find this? So this polynomial, if I call it p of x, it's equal to this times this. So if I divide this by this, I should get that. So I'm going to do long division. Please stop me and ask if you don't understand anything. If anything is confusing to you, please stop me and ask. I am just doing this thinking that you can remember everything that we've done in the past. I expect something in the form ax squared plus bx plus c, the quadratic. Let's divide this. So I only look at this. I get x squared here. Look at this. And this has to divide without a remainder, because it factorizes completely. This is the product of these two. Here I go. I get no remainder. So there's my other factor. X squared minus 2x minus 3 is my other factor. And how do I now proceed? This is my equation now. So here I can, so this is already given to me, so I don't have to proceed with that. Or I equate each factor to 0. So I get the, I'm just showing you this side. This is, this part, we know it already. So we don't need that. We just have to proceed with this. How do I solve this quadratic? Again, it doesn't look like it factorizes nicely with real numbers. So let me use the formula. Or to solve this, I will use the formula. Let me change the color. To use the formula, A is 1, B is minus 2, and C is minus 3. Two, B squared is 4. What do you get in the root, inside the root? Oh, does it factorize? It factorizes, no? You don't need this. Are you disappointed? All solutions are real here. Okay, this factorizes. This factorizes to x minus 3, x plus 1. No? So the other two are x equals 3 or x equals minus 1. So all the three, therefore, the three solutions are x equals minus 4. They had given that x equals 3 or x equals minus 1. The reason why I have embedded this example in here, because this has nothing to do with complex numbers, all the roots were real, is because for the example 3, you would need this. I mean, this is just to remind you of this technique that we use from algebra, polynomials knowledge. When you know one solution, you can use that to think of the factor, and you can figure out the other factor and go on to solve the equation. I wanted to remind that through this example. Let's look at the third example now. Can I change this screen?
Miss, not yet. Give me a second.
Okay, no problem.
The three solutions are okay. That's it, Miss.
Okay. Example 3. Given that 1 plus 2i, I'm putting a bracket just to like keep it together, okay? 1 plus 2i, given that 1 plus 2i is a solution of z cube. This is similar to the earlier. 4z cube minus 11z squared. This is similar to the previous one, but the given solution is not a real solution. It's a complex solution. 11z squared plus 26z minus 15 equals 0, comma. Find the other solutions. Find the other solutions. Now, what? Okay, I'll give you a moment to think about this. Don't do anything. Don't write anything. Tell me what comes to your mind. What you think? What you're thinking of? Very good, Hatri. Sorry. Immediately, you can give another route, another solution. Immediately, you don't have to do anything.
Yeah, factor out.
Not like earlier. Huh?
factor out an x.
Factor out?
An x.
The conjugate of the solution
Yeah.
is the
What?
solution, right?
Yes,
Oh,
yes,
yes.
yes.
Yes. Oh,
Yes,
no.
Netri, yes, Malit.
Malik.
That was Malit.
Yes, Malit.
Yeah.
Yeah, I said Netni because Netni also gave the answer. Nathan, you can't factor out Z here. It's how do you factor out Z?
No, I was
so
thinking of the previous example. I forgot about the conjugate.
Even in the previous example, we didn't factor out. What do you mean by factor out? And
Now I'm going to turn this thing into, now this is to the power degree 3 now, miss. I'm going to turn the biggest power to the degree 2 over there. Basically, I'm going to turn it to a quadratic. I'm going to make it a quadratic and a linear. But it's
we are
okay.
not turning this.
Yeah, I realized my mistake. It's okay. It's okay. It's okay.
It's okay. Are you sure? We can't
Yes.
turn this into a quadratic. What we can do is factorize this into like earlier what we did was, now don't think we turned our equation into a quadratic.
We make them.
This is cubic. This is still cubic. This is the product of a little linear polynomial and a quadratic polynomial. This is still cubic. And then these are the two factors, and you equate each factor to 0, and then you get like little new equations.
Right.
Don't mix things up, please. I hope you're not mixing things up.
No.
In this case, one solution is a complex solution. And from the theorem 2 we had earlier, we can immediately say, oh, if 1 plus 2i is a solution, 1 minus 2i is a solution. How do we know? From the theorem. Okay. So let us write that. We can say, here's the answer. This is the answer I'm writing now. Answer to this. If 1 plus 2i, did you check whether the coefficients of this polynomial equation are real coefficients? They are all real. 4, minus 11, plus 26, minus 15. The coefficients are real. That theorem applies if the coefficients are real. If 1 plus 2i is a solution, 1 minus 2i will also be a solution. So we now have 2 solutions. We only have to find one more. Because it's a cubic equation, only one more we need. Will also be a solution. Now, think of this as a problem given to you. Okay, this is problem solving. We have 2 solutions. It's a cubic equation. How do you find the third one? I would like to give you a few minutes, because if you can, I mean, you just have to think of everything that you know, okay? Apply the tools, apply the knowledge that you have. That's all you have to do. We wouldn't be doing anything new here. It's just that we are working with complex numbers. Just think that this is a real number. Just for a moment, think this is 3 and this is 4. The 2 solutions are 3 and 4. And we want to find the third one. I will give you a few minutes. How do we find the third solution, third root? Think of what we did earlier.
You equate the 2 solutions to z, and then you make two.
You equate, say it properly, Malik. You
You
equate what?
equate the two solutions to z. Like z is equal to 1 plus 2y.
Huh?
Z is equal to 1 minus 2y, and then you take all the terms to the other side. Like so, it basically becomes then z minus 1 plus or minus 2y, and then you multiply those two out. Can that work?
I'm not sure whether I understood what you said.
Miss, you just write what you got, and then I'll tell like what you want.
Part of what you said sounded like what we are supposed to do, but part of it didn't make sense to me. The first part, Hatvi saying,
Miss, can we divide?
Again, Hatvi, what Hatvi is saying also sounds like, Hatvi, can you put that to everyone, please? Tarindu, was that you talking?
Yes, Miss.
Hello?
Yes, Miss.
I can't hear you properly. Everyone read what Hatvi is saying. Okay, so Malit is saying, yes, Malit. So Z is equal to 1 plus 2y is a solution. And also Z is equal to 1 minus 2y is a solution. What this means is, before I come to what Hatvi has said, okay, I'm talking about what Malit is saying. So Malit is saying Z is, this is right. These are solutions means this Z could be this or this, okay? So if I write this polynomial equation as P of Z is equal to 0, where this is P of Z, where I call this as P of Z, then if I substitute 1 plus 2y in it, it will be equal to 0. Or if I substitute 1 minus 2i in it, it satisfies the equation. It fits into the equation. That's the meaning of a solution. But then make it. No, that's right. That's correct, Malik. That part I didn't hear when you were saying it. Now, Hatvi, I'm sure what you are saying is also the same thing, but you are just saying multiply 1 plus 2y and conjugate. You don't multiply these two. That's not what you multiply. Now wait, okay? Yes, right? If these two are two roots, if this and this are two roots of this equation, that means this equation is 4z cubed minus 11z squared plus 26z minus 15 is equal to 0. Na? And then this is a solution means I know a factor of this polynomial. What is the factor? It's hard to write. I mean, it's hard in the sense this is a solution. I know two factors. And then I need another linear factor here. But I have two solutions means I know two linear factors of the equation. How do I write it? Suppose this was just a real number, like this was 3. If 3 is a solution, what would be the factor? Can someone say it? Nathan? If x equals 3 is a solution of an equation, polynomial equation, some p of x equals 0.
Okay.
That means we know one linear factor of the polynomial p of x. What is that factor? If x equals 3 is a solution, Neti, you're right.
X equals 3 is a solution.
Huh?
If x equals 3 is a solution, then
If x equals 3 is a solution, that means da is a factor. What is the da? No, Tarindu. If x equals 3 is a solution,
I don't know.
We used that now in example 2. Can you go back and look at that? If x equals 3 is a solution, x minus 3 is a factor. This is P3 first lesson.
Ah, okay. So if that is 3, that means x.
If you start with a quadratic equation, some quadratic equals 0, and you factorize this to x plus 9 and x minus 7 equals 0. This means x is equal to minus 9 and x is equal to 7. Now go back. If x equals 9 minus 9 is a solution, x plus 9 is a factor. If x equals 7 is a solution, x minus 7 is a factor of that polynomial you had here. This is O level then. Okay, so here, if this is a solution, then z minus that number, which is 1 plus 2y, is a factor. And if this is a solution, z minus that solution, 1 minus 2i, is a factor. Now I can multiply these two out. This is a linear factor. This is another linear factor. So I need another linear factor to complete this. This is a cubic. A cubic can be broken down to 3 linear factors. 1, 1, 1. That combines to 3. And if I multiply these two out, if I multiply 2 linear factors, that will give me a quadratic. 1, 1 combined to give 2, degree 2. So if I multiply these two, I would get one big quadratic factor times this linear factor that I'm trying to find, because this other factor would lead me to the third solution. Can you find what you get here? The quadratic. Then we can divide this by the quadratic linear factor. Okay. So multiply these two. I'm going to do it on the side here in a different color. Oops. I'm multiplying z minus 1 plus 2i. This just looks complicated because our numbers are now complex numbers. You have 1 plus 2i instead of just having like 3. That's the only, like, it's on your eyes, it looks very complex because the numbers are complex. But what we are doing is the same thing that we would do with real numbers. So I want you to always like think about that. Okay, don't let the complexity in the symbols intimidate you. Now carefully multiply this out. That's what I get. Now let me simplify that. See whether this is what you get. That's correct. Normal way, yes, it's the same thing. Yes, Natni. So we have figured that this is, this is a quadratic, and then the other one is a linear factor equals to 0. If we divide the original polynomial by this quadratic, you will get that linear factor. And by equating that to 0, you can solve it. You can find the third root. I'm going to call this P of Z by the quadratic factor. Z minus. Okay, let's see. Natni has given me the last. Then that would be, yes, Natni. Let's see. I'm not sure whether that, yeah, that must be correct. Yeah, correct. So you would have, I have to change the screen, go to the next screen. So 4z cube. Sorry. 4z cube minus 11z squared plus 26z minus 15, I will divide by z squared minus 2z plus 5. Dividing by this. So I only have to look at this and this. I get 4 here. What's that?
For Z nomis.
Yes,
Yeah.
Nathan. Very good. So I will let you do it, okay? So you do this and see what linear factor you get here. What do you get here? So continue this. Shall I do it? Or you got this? You got this. What is this? 4z minus 3 you will get. Okay. So that's enough. I will just therefore the third root, therefore the third solution. You get that by you equate your third factor 4z minus 3 to 0. So z is equal to 3/4. That's a real solution. So this cubic equation has one real root and two complex roots. And the two complex roots are conjugates of each other. How did I equate this to 0? Because my equation is, that was my equation. I had a quadratic here. And this was my linear. This is this one. You equate each factor to 0 and solve, right? So that's what you do. If you want, you can finally write all the three solutions together. Therefore, the three solutions are z equals 3/4, z equals 1 plus 2i, and z equals 1 minus 2i. These three numbers satisfy that equation. If you substitute any of these numbers into that, the equation will be true. You put it into the left-hand side, it'll be equal to 0 because you had 0 on the right-hand side. They're satisfied, okay? So questions like this you can get with polynomial equations who has complex solutions. And you have to combine your polynomials, knowledge, factors, all that to go about it, along with those two theorems, especially the second theorem. If a complex number is a root or a solution, its conjugate will be a solution. You have to remember that. That's a theorem. I will give you your break now. And then what we are going to look at next is a very interesting one.